Welcome to the last lesson in this chapter about implementing module communication, and I want to wrap it up with a discussion about eventual consistency. Here is our quick agenda for this lesson. We're going to discuss dealing with eventual consistency in a modular monolith and in general in distributed systems. Then I want to highlight a few key points about eventual consistency between modules and why it could actually be very acceptable. And I want to stress the importance of maintaining consistency within a single module. So let's start our discussion to highlight where eventual consistency occurs inside of our modular monolith. I'm looking at the registered user command handler, and this implements our simple use case for creating a new user in the system. The create method is going to raise the user registered domain event. We are using the domain event pattern to decouple the business logic of our main use case, which is registering a new user, from any side effects that could occur when we handle the user registered domain event. We can see one of those side effects in the user registered domain event handler, where we are publishing an integration event. A few other examples of what we could do with the user registered domain event is to send them a welcome email, so this would fall under notifications. Maybe we could set up a loyalty program in a different module to incentivize users to continue purchasing more tickets for events. And in this example, after we have published our integration event, we need to handle it, and in the ticketing module, we have a respective handler for this integration event where we could do anything we like. In this case, we are duplicating the user's data into a customer record, which is how we are referencing the user inside of this bounded context. So again, what is our reasoning for implementing communication between modules like this in an asynchronous fashion and embracing eventual consistency? First of all, we are decoupling the primary use case inside of the user's module in this example from any side effects inside of the other modules that we also need to occur. Secondly, this is a very flexible approach. When we want to introduce new behavior in our system, in the user module, we can just add a new domain event handler and introduce the behavior there. In the other modules, we can register a new consumer for the user registered integration event, or any other event for that matter, and start implementing a new business functionality. If we wanted to implement something like this with synchronous communication, it would be much more difficult and much more cumbersome. We would need to write a lot more code, orchestrate between the different modules to achieve the same result with what we can do with a few simple message handlers. So what is the price that we are paying to have all of this flexibility? Well, I'm throwing this term around, eventual consistency, but what I really mean by this is there is a given period of time where the user's module is consistent, and we still haven't persisted the new state inside of the ticketing module. Within that period of time, however long it is, no business functionality is going to work that depends on the message being handled. In this case, we would need the customer to first be created in the ticketing module before we can go ahead and add items to the cart or create a new order. Another aspect is how do we make sure that whenever we publish an event, it always gets consumed. When you start thinking about this problem in depth, you may come to the conclusion that this is practically impossible. And this is because of the very nature of how distributed systems work. So what can we do to improve the reliability when it comes to publishing and consuming messages? I said that we are going to solve this in a separate chapter that deals with the outbox and inbox patterns, but essentially what it's going to come down to is persisting the domain events inside of an outbox, which is going to allow us to store our domain events in a transactional way, and then we can publish them out of process asynchronously, one by one, while managing exception handling and also being able to retry a publish if it fails for some reason. And then on the consumer end, we can persist an incoming message into an inbox to make sure that it is stored inside of our module, and then we can process the message also in a background job and trigger the behavior that we need. And this also gives us many of the same benefits. We can control exception handling, we are able to retry this message multiple times, and it even gives us the ability to replay the outbox and inbox messages in the future when we need to implement a new handler for those messages. Now, to be able to do this, we also need to think about idempotency, which is another topic that I'm going to discuss as part of a future chapter. I don't want to continue this discussion much further because this is a very rich topic, but I do want to discuss maintaining consistency inside of a single module. So let's take the use case of creating an order. And I want to note that I added a bunch of new use cases to the solution, so if you want to grab the updated source code, it's going to be under this video. Now let's take a look at the create order command handler. You will see that I have a lot of new dependencies here. So a customer repository, an order repository, a ticket type repository, a payment repository, and a payment service because I'm implementing mock payments for my order. Now let's take a look at the handle method and see what we have inside. The first thing you're going to see is creating a new database transaction. And this is one of the things that's going to help us make this operation atomic. Then we're going to fetch the customer, create a new order, get the cart for the current customer, and then once we have the cart items, or rather we have confirmed that the cart isn't empty, we're going to fetch the ticket types using the ticket type repository. And there's an interesting method here called getWithLockAsync. I'm going to explain what this does in just a moment, but after we have the ticket type, we're going to update the available quantity based on the current quantity in the user's cart. Because we are initiating a ticket sale, we have to reduce the available quantity. And note that this operation could also fail if we don't have enough available quantities. So this is also a validation that we are doing here. If all goes well, we're going to add the item to the cart, add the order to the repository once we have added all of the items, and then we're going to fake a payment to the payment service by charging the order's total price. This is going to return a dummy payment response, but you can imagine that this would be integrating with a payment gateway. And let's say I create a new payment record, insert this to the payment repository, and finally I'm going to persist everything in the database by calling save changes, finish the transaction by calling commit async, and I'm also going to clear the customer's cart. There are two remarks that I want to make here. First of all, calling the payment service like this. Typically, this would also be done asynchronously. So what you would do is first create the order, then attempt to charge the customer as a separate operation. And if that succeeds, you're going to confirm the order. And if the payment fails, we can just cancel the order. Now in this example, to make things simple, I'm initiating the payment while also persisting the order. But I wanted to highlight that there is a more robust way to do this in a real world scenario. Now I want to go back to the getWithLockAsync method to show you what's going on here. I said in a comment that this acquires a pessimistic lock or frozen exception. Let's take a look at the implementation. I'm using EF Core 8's raw SQL queries feature to be able to select my entity by providing a SQL query. The string interpolation that you see here to specify the identifier as part of the string isn't suspect to SQL injection because this is actually a formatable string. And what's going to happen here is this identifier is going to be converted into a SQL parameter that EF Core can properly parameterize in the query. But the interesting part is I'm issuing a typical select statement, filtering based on the ticket type identifier, and I have this for update no wait statement inside of the query. What this is going to do is lock these rows inside of my Postgres database immediately as part of the current transaction. This is triggered by the for update clause. The no wait clause in our query tells the database to simply not wait if this row is already locked. In that case, it's going to throw an exception and we would have to retry the entire operation for creating the order, which is not something I'm handling in this case, but I want to highlight it so that you know what would be the proper way to implement it. An alternative could be removing no wait, which would cause this query to wait for a given time and try to acquire a lock on this row, but in this case you could run into a timeout. And the reason I'm doing this is because of concurrency in our system. I want to prevent any other customer from reducing the available quantity on this ticket until I'm able to place the order. This does mean that some customers will run into issues when placing an order, but it's nothing that we can't solve with a few retries in the create order command handler. There are a bunch more new use cases that you can explore inside of the project that I added behind the scenes, and I'm going to add many more use cases as we continue developing this project. And with this, I'm going to wrap up our short discussion about eventual consistency and, in general, managing consistency within a single module. Our next lesson is going to be part of a new chapter where we are going to implement authentication and authorization inside of our modular monolith.